Mars is back in the spotlight as NASA once again focuses on unraveling the mysteries of the red planet, this time with a new rover called Curiosity. During the lead-up to this mission, there was a lot of talk about the so-called 7 Minutes of Terror, which referred to EDL, or the Entry, Descent, and Landing Stage. The reason the word terror was used is because researchers spend years of their lives developing and perfecting a spacecraft, only to have this very short 7-minute window often determine whether the mission fails or succeeds. During these 7 minutes, the spacecraft experiences enormous changes in temperature, pressure, and speed. But surprisingly, even with the tremendous amount of data and experience we have about how to land on Mars, there is still a gap in our knowledge about exactly what a spacecraft experiences during the crucial EDL stage. But beginning with the Curiosity mission, NASA researchers have developed a suite of instruments that will give us a much better understanding of the EDL conditions, changing that 7 minutes of terror to something more like 7 minutes of heightened concern. Coming up on this episode of NASA X, we will find out about the challenges of EDL as we follow the MEDLI team in their quest to improve our understanding of entry, descent, and landing. We will follow them from some early setbacks and design challenges all the way through to the triumphant night that Curiosity landed on Mars. In this small clean room at NASA Langley, researchers are lovingly and carefully putting the finishing touches on this device that is part of MEDLI, or the Mars Science Laboratory Entry, Descent, and Landing Instrumentation. This very device will eventually meet a fiery end, more than 350 million miles away on the surface of Mars. For most of us, the idea of our hard work ending up battered and destroyed so far from home wouldn't sit well. But this team is okay with the end result, because once MEDLI completes its job, our knowledge of how to land on Mars will have increased dramatically. Mars is a curious place. With our modern tools, we have a much better understanding of the planet, but attempting to understand Mars has long been a pastime for both early humans and for us today. Observers from around the world have long viewed it with awe, seeing its red color as being both ominous and also a symbol of strength. The name we use today for Mars comes from the Roman god of battle, but the Romans were not the only culture who noticed Mars. Ancient Egyptian observers admired the planet so much that today's capital, Cairo, comes from the ancient Arabic word for Mars, Al-Kahira. Most early cultures considered Mars to be aggressive or evil due to its red color. And each mission we've sent to Mars has done little to dispel this perception. In addition to its cold and barren landscape, it is incredibly difficult to safely land spacecraft there. In fact, out of the first 41 missions to Mars, only 15 were successful. Even though difficult, when missions are successful, they provide immense amounts of data that can be used to further our knowledge for years to come. One of the most successful early NASA programs was the Mars Viking missions in 1976. That mission landed 2 stationary landers on the surface of Mars, and although they were only scheduled to last for 90 days, the landers transmitted data for several years, prompting one NASA observer to say, "We found intelligent life on Mars, and it was us." Other missions followed, some successful, some not, but with each mission, our knowledge and experience delivering vehicles to Mars increased significantly. Building on both the successes and failures of the past, NASA decided to send the most complex and technologically advanced mission that had ever been sent to Mars, called the Mars Science Laboratory, or the Curiosity Rover. The size of a small car, this rover has enough scientific firepower to unlock many of the mysteries of Mars in ways we could only have dreamed of a few years ago. But getting the Curiosity Rover there would be tough. This vehicle is much bigger than anything we have ever tried to land on Mars before. The rovers and landers of the past were all relatively small, so with minimal changes, researchers could generally fit each new payload into a similar-shaped aeroshell and use an existing thermal protection system. Because these factors didn't change much, researchers had a known commodity and could plan accordingly. Curiosity is different. It is by far the largest and most capable rover to ever land on Mars, and researchers had to completely rewrite many of the How to Land on Mars books.
We're limited by how large a vehicle we can put in the launch vehicle by the launch vehicle shroud. So those other vehicles flew on smaller rockets to save costs. They weren't taking as much mass, but they then were limited to a 2.65 heat shield. With MSL, we're flying the biggest one that we have to date, about 4.5 meters, and that's about as big as we can make it on any rocket we have. So this is a very large heat shield. Why does that matter? Well, size matters on these heat shields because the larger the heat shield is, the more drag it produces, and that drag force is what slows you down. So the more drag you have, actually the more mass you can put in it. And so we're taking the biggest thing we've ever taken to Mars. It's like a car. It's a metric ton, 2,200 pounds, basically, of vehicle that we're going to land. And so we needed that big heat shield to be able to slow us down to get to the surface.
To get to the surface safely, researchers had to develop a completely new aeroshell, new thermal protection systems, new sky crane landing sequence, and so much more, leading to a lot of uncertainty in the research community. Because the entry into the atmosphere, the descent to the ground, and the all-important landing are some of the most important elements to safely getting any vehicle to Mars, especially one that is much larger than previous vehicles, there has been a big push to better understand the specific conditions that the vehicle will face when entering the Martian atmosphere.
The Mars atmosphere is, too thick to ignore and too thin to really help you out too much. And that's why landing on Mars is so challenging. The pressure differences and the density differences, along with the chemistry differences, the Mars atmosphere is mostly carbon dioxide as opposed to our nitrogen-oxygen atmosphere here on Earth, that it's really difficult to simulate and it's difficult to test in, nearly impossible. So we do different tests in different facilities trying to piece together the story and validate our simulation. So if it works at this point and this is the model, then we think that the model will work over at this point, which is the real flight environment. But it's a very involved, complex process to design and ensure that a vehicle will perform as we think at Mars.
So one of the challenges that we face is the lack of data on how vehicles perform in the Martian atmosphere. So that's one of the main problems. Been very little instrumentation on previous missions. MEDLI is the most complete instrumentation data set we will have on an entry vehicle at Mars.
For past missions, researchers would simply over-engineer pieces to make sure they worked as expected, which of course added weight and complexity to each mission. But as we begin to think about landing humans on Mars, we need to have more precise readings and understanding of the exact conditions spacecraft will face when they enter this alien environment. One way to get these measurements is to place sophisticated sensors in the heat shield itself. This sounds simple in theory, but it is in fact very difficult. To do this, NASA put together a highly skilled team of engineers to tackle this looming problem. They came up with a concept called the Mars Science Laboratory Entry, Descent, and Landing Instrumentation, or MEDLI, as the solution.
So MEDLI is a unique opportunity for us. We've been in the technical community wanting to instrument an entry vehicle for as long as I can remember, and finally all the stars aligned and we were able to do it. So we're pretty excited to be able to give this data set back to the engineers and the scientists. MEDLI is a series of sensors on the Mars Science Laboratory heat shield. So we've actually mounted pressure transducers to the inside of the aeroshell structure, and we've put plugs in the thermal protection system material to measure the pressure and the temperature on the spacecraft as it flies down through the atmosphere.
MEDLI consists of two unique sets of instruments to help gather this information. The first is called MEDS, or the Mars Entry Atmospheric Data System, and the second is known as MISP, or MEDLI Integrated Sensor Plugs. MEDS will measure the atmospheric pressure on the heat shield to see how well models predicted the spacecraft's real trajectory and its aerodynamics, while MISP will measure how hot the heat shield gets and how much of the heat shield burns off during entry. Both of these instruments will be attached to the heat shield section of the spacecraft and will experience the highest temperatures and pressure that will be exerted on the craft. Engineers have determined that the best configuration to get the measurements would be to place the 7 MEDS pressure transducers in a cross-shaped configuration to help calculate the vehicle's angle of attack, side slip, and dynamic pressure.
The other part of the MEDLI system is the thermal plug, and this is actually made of the Pica heat shield material, and it's about 1¼ inches in diameter, and it's bonded into place, and then the wires come through the structure and again feed back to our electronics box. So with these plugs we have 4 thermocouples measuring the temperature in depth in the material. This is important because that will tell us how the material responded to the heat pulse and how it soaked through and at what rate. We also have a recession sensor, which is the little dot right there off center. It's called a heat recession sensor, pun intended, and it will sense the recession or how far the material burns away as we enter the atmosphere.
So with this plan in place, the MEDLI team began working on the problem of how to integrate these systems into the spacecraft. Immediately, the team knew that they would have to drill holes in the heat shield of the MSL to insert these plugs. As you can imagine, with a $2.5 billion mission, there was some concern about drilling holes into a perfectly good heat shield.
There's a lot of consternation because it's kind of like jumping out of a perfectly good airplane. You have to keep in mind the four-body heat shield, all the TPS typically, is a single point of failure subsystem for the entire mission. So taking a single point of failure subsystem and then putting holes in it gets people excited. And that was one of the ongoing challenges to this project was to demonstrate at every turn, under every experience, that the holes for making pressure measurements and the holes that we would have to make in to put the thermal plugs would be okay. It would be no threat to the project. And so we were very successful in doing that.
With the go-ahead to begin, the testing phase soon followed. Of course, one of the main tools used in the initial testing were computer simulations. By the time of the launch, millions of simulations had been run to make sure everything would react as anticipated. With the computer data as a starting point, the next big step would be to test the sensors in environments that were as close to real world as possible. At the beginning of the process, it was determined that the heat shield would be made from the exact same material used for every Mars mission since the Viking landers. With this knowledge, the team began building the plugs and then placing them in a unique facility called an arc jet. This facility creates temperatures in excess of the temperatures that will be seen on Mars. After months of successful testing and data in hand, the team was ready. But then there was a problem. After some intense examination, it was determined that the material they were using may not be suitable for this mission, so a change would have to be made.
The reason behind that was because the original material, and this is the example of that, it's called SLA 561V, it's a cork. And cork-based material with a lot of other soupy kind of elements in it, in a honeycomb matrix. That material was invented for the Viking program. And the Viking program was experiencing roughly 15 watts per square centimeter. The architecture of how that mission got to the surface of Mars was completely different than MSL's, in that they went to orbit around Mars and then gently went down to the surface, whereas MSL did it in one single shot from the 13,000 miles per hour then back down to the surface. So further calculations and experience showed us that there was a shear flow that was happening because of turbulent flow was also being predicted. And when we used the best capability that we had for ground testing, this material actually just dissipated and went away in ground tests. So then very quickly the heat shield for MSL became the #1 threat to the entire mission.
With the mission hanging in the balance, the team changed to a new heat shield material called PICA, or phenolic impregnated carbon ablator. This material had only been used once before on the Stardust mission, but it had worked phenomenally well. With this new material in hand, the team started the testing process all over again. More arc jet testing was ordered, and the material passed with flying colors.
This is a fairly light material. This is about, the density would be about 1/10 of a ceramic material, even much lower than a metallic heat shield. So this has a pretty high temperature capability. This can go several thousand degrees, and there is no melting, it's just sublimes. And the primary way it rejects heat from the vehicle is through re-radiation. As it rises in temperature, it re-radiates back into space. All the heat, that's the primary way it rejects heat. Another way of rejecting heat is actually pyrolyzing the material, which is why it becomes black from the original color. And that's the secondary way of rejecting heat as well.
More testing followed, including calibration of the MEADS instrumentation on a small-scale model of the craft that was fired from a cannon at the Aberdeen Proving Ground. That test also came back in the affirmative. So with all the data in hand, it was now time to begin drilling the holes in the heat shield and placing the instruments on board. Once the MEDLI device was installed, the heat shield was attached to the vehicle and in short order would soon be on its way to Mars. On the morning of November 26, 2011, the team watched as the Mars Science Laboratory mission launched for Mars. All they could do now was wait, an agonizing 9 months to see if all this hard work would pay off. On the evening of August 5th, 2012, the team begins to arrive at JPL. Spirits are high as they move toward the EDL room. There's a lot of tension, but everyone feels confident the mission will be a success.
Maybe a little anxious, but not as nervous as we thought we'd be at this point. We've really done the testing and looking at it. We're ready for this thing to happen.
As the team begins to take their seats, the tension in the air rises. With Mars hundreds of millions of miles away and the data traveling at the speed of light, it still takes about 14 minutes for the information to come back to the EDL room. As engineers and researchers watch the screens, all the data they receive has already occurred minutes before.
In about an hour and a half, we'll get our last health status, and then we'll get a few points of data, and it'll say, okay, this is the state of the MEDLI instrument before entry. And then at 30 minutes, then we'll get the real data. So it'll be exciting.
With the success of the mission on the line, nerves and excitement can be seen everywhere. With just minutes to go before landing, data begins to trickle in.
That we have seen heating of heat shield through the MEDLI instrument. Everything looks fine, which is as expected.
MEDLI instrument.
The first data sets are good, But with about 13 minutes to go before landing, the realization sets in that the MEDLI instrumentation has already worked or failed on the Martian surface.
The spacecraft is actually on the surface at this point because there's a 14-minute lag. So we're not going to know for sure. It's on the surface one way or another.
Data continues to come back.
We have a new data set.
Parachute, what? Parachute. We are in powered flight. Sky crane has started. Descending at about 0.75 meters per second as expected. Touchdown confirmed. We're safe on Mars.
You know, we was performing nominally the whole way through as near as we could tell. Very good day.
I think we just accomplished something incredible as a team. NASA, this was something many people looked at the architecture and said it couldn't be done, and shouldn't be done, but we did it and successfully got that rover on the surface. So we've got a 2-year mission to determine if Mars could have or even could currently support life.
You guys got it there, and now it's a wealth of data for us. And next mission, we're going to do even better.
This has been quite a night for the team, but only a fraction of the data has been received. Most of the information for the landing has been stored on board the Curiosity Rover. The MEDLI team will receive all the data over the following few weeks.
Everything went flawlessly. We got our data back. It's clean. We saw the sensor performed according to expectation.
We have the entire data set back. Everybody is extremely happy, and we can see that all that hard work that has gone into it has really paid off. And the data set is rich, and it will be something that the community uses for literally decades to come.
With the data back and MEDLI a huge success, MEDLI type instrumentation may become the norm for receiving data back from future spacecraft. This type of information will become even more important as we begin to plan for human-rated missions to Mars and beyond. With each small step and knowledge captured from tools like MEDLI, we will continue to get closer to that one day when humans walk on the red planet.